All right, the think and discuss. Although you don't know it, this is take 2. So 79, in answer to the question, what keeps the Earth moving around the sun, a friend asserts that inertia keeps it moving. Discuss and correct your friend's erroneous assertion. So there's 2 pieces here. One, this idea of what inertia is. Inertia is a concept from my point of view. Inertia is the property of an object which tells us that an object in motion will stay in motion at a constant velocity. An object at rest will stay at rest unless acted on by a net outside force. This is all summed up beautifully in a math form in Newton's second law, but Newton's first law just keeps the words there. So once the Earth starts moving, what keeps it moving? Well, nothing really keeps it moving. So it's not like inertia keeps it moving. The Earth has inertia, and which just means that it's going to just keep moving. Now, the other aspect of it is around the sun. Now, the velocity, which we get into in more detail in Chapter 3, velocity is how fast an object's going and in what direction. Now, the direction that the Earth travels is sort of a circle. It's really an ellipse, but it's close to a circle. So if the Earth is traveling in a circle, that means the direction is constantly changing because it's traveling like this, and then my finger points in a different direction as the Earth goes around. The direction changes, and therefore the velocity changes. If the velocity changes, there must be a net force acting on it. This we get into in more detail in Chapter 8, but the idea that in order for the Earth to actually go around the sun, there must be some force acting on it, and that's the force of gravity. Now, there's a formula that we will first use, the force of gravity, that weight is equal to mg. This, when you start getting to the astronomical aspects, when you start dealing with outer space, that formula becomes a lot harder to work with, and so there's another formula we get to in chapter, I think it's 9. So, but there is a force of gravity between Earth and Sun as the Earth goes around the Sun. That's what keeps it going around the Sun, the force of gravity. What keeps it moving? It's already started. At some point, it started moving in that direction, and so there's nothing that really keeps it moving. It's the force of gravity that keeps it moving around the sun. All right, number 82. Suppose you're in a moving car and the motor stops running. You step on the brakes and slow the car to half speed. If you release your foot from the brakes, will the car speed up a bit, or will it continue at half speed and slow due to friction? Defend your answer with your discussion partners. So presumably you have discussed this well with some friends, family, the dog. And so when you remove your foot from the brake, if you think about the forces acting on it, on the car, we have friction between the car and the road. We have friction between the brake and a brake pad and the disc. Depends on what kind of braking system you have. And weight and normal force. Now, weight and normal force, we are making the assumption that this car is moving on a horizontal surface. Weight and normal force are perpendicular to the motion, so we're going to ignore those. They'll neutralize each other unless the car is going uphill or downhill. We don't need to worry about those. We are assuming it's moving on a horizontal surface. When you slow down, you are basically converting some of the kinetic energy of your car. And yes, I know these are chapter 7 terminology. I should not be using them, but I'm doing it anyway, so there. So it's converting some of the kinetic energy of the car into kinetic energy of the air molecules. In other words, things get hotter. And that takes away some of the energy, it takes away some of the speed. So in terms of force, it's a friction force that slows it down to half speed. And so at this point, when you take your foot off, you've removed a great deal of friction by taking your foot off the brakes, and so now it's just going to be friction between, just the natural friction between the axle and whatever the axle sits on, I'm blanking right now, and the tire and road. We talked about in a earlier problem about something rolling, that when it get a depressed surface, that surface is going to depress some, and probably the tire more than the road. But there will be some rubbing there, and that's where there's going to be some loss. So you will slow down. It should travel roughly the same speed for a while. It depends on how new the car is or how expensive the car is. The more expensive cars, you should take your foot off the brake, and it should coast very nicely. The cars that I buy, it starts slowing down immediately because, well, that's where I am. Number 90, you toss a coin straight up while riding on a train. Where's the coin land when the motion of the train is uniform along the straight track? Remember that if I'm on a train and the train's going 50 miles an hour, I'm also going 50 miles per hour relative to the ground. I'm going 0 miles per hour relative to the train. So if we say a train is moving relative to what? So generally we think about in terms of the ground being still, but in physics we don't necessarily take that for granted. So in this particular problem, let's do it from the point of view of you, or the train itself. The train is not moving relative to you. You're not moving relative to the train. You're just sitting there. The coin in your hand is just sitting there. So if I toss this thing up into the air, it's like the train's not even moving because you're moving with it. And so the coin just go up and down. Now, the second part of this is if the train slows down. So if I toss the coin in the air, remember that I give it an upward velocity here, but there was a horizontal velocity relative to the ground, a horizontal velocity relative to the ground of, let's just say 50 miles an hour. Now, if the train starts slowing down, that coin still, once it leaves my hand, it still has that horizontal component of 50 miles per hour, whereas the train initially going at 50 miles per hour and they're staying together, start from over here, it's going together. But if the train slows down, let's make this the coin, this thing is going up in the air still at 50 miles per hour, and the train starts slowing down, and so the coin is now going faster than the train. And therefore, the coin, if the train slows down, the coin should land in front of you. And that's that.